Welcome back to our system design series. Today we tackle one of the most essential and complex problems in modern software architecture, designing a large-scale payment system. Whether you're building an e-commerce platform, a marketplace, or a financial service, the ability to securely and reliably process payments is critical. But scaling payments isn't just about charging a credit card. It involves orchestrating transactions across multiple services, ensuring regulatory compliance, preventing fraud, and maintaining financial accuracy down to the cent. In this video, we'll walk through a robust production-grade architecture for a global payment system. We'll explore key components like payment services, payment executors, wallets, ledgers, and third-party payment service providers, PSPs. We'll also cover both pay-in and pay-out flows, security considerations such as PCI compliance, and mechanisms to ensure exactly once delivery and system-wide consistency. By the end, you'll have a deep understanding of how to design a secure, scalable, and fault-tolerant payment infrastructure that can process millions of transactions per day without breaking a sweat. Let's begin with a clear problem statement and dive into the requirements that shape such a system. The problem is to design a large-scale payment system for e-commerce. Here are some good requirement questions to ask. What kind of payment system are we building? What payment options are supported? Do we handle credit card payments ourselves? Do we store credit card data? How many payment transactions per day? Do we support payout flow? Let's walk through the high-level design of a large-scale payment system that supports secure and reliable money movement across buyers, merchants, and financial institutions. At the heart of the system is the payment service, which acts as the orchestrator. It accepts payment events initiated by users, for instance, when a buyer places an order, and coordinates the entire life cycle of the transaction. Next, we have the payment executor, a stateless service responsible for processing individual payment orders. It interacts with external payment service providers, PSPs, such as Stripe or Adyen, to actually move the money from the buyer's funding source to the platform's account or the merchant's account. Behind every PSP sits a card scheme like Visa or MasterCard, which handles the routing and authorization of credit card transactions. To ensure accurate and consistent tracking, the system maintains a double-entry ledger. This is a foundational accounting practice where every transaction is recorded in two places, a debit from one account and a credit to another, and the sum must always be zero. This model helps with reconciliation, fraud detection, and regulatory compliance. Each merchant has a wallet, representing their account balance within the platform. When money is collected from the buyer, the wallet service updates the merchant's balance. Then, the ledger service records this in the financial ledger for auditability. The system relies on two core data models: the payment event table, which stores high-level payment requests and customer metadata, and the payment order table, which tracks the status of each discrete payment transaction, including if the ledger and wallet have been updated. The pay-in flow begins when the buyer triggers a checkout. The payment service logs the event, and the executor processes it through a PSP. Once confirmed, we update the merchant's wallet and then the ledger. For the payout flow, money moves in the opposite direction, from the platform's account to the merchant's bank account, usually via a third-party payout provider. Finally, to meet compliance and PCI requirements, many systems integrate with hosted payment pages. These are embedded widgets or iframes provided by PSPs to handle sensitive payment data securely, reducing the platform's exposure to risk. This architecture ensures scalability, auditability, and robust failure isolation across components, all of which are crucial for financial systems operating at global scale. This slide outlines the steps involved in processing a payment using a payment service provider, PSP. Let's break it down. Payment service call. The client initiates the payment process by calling the payment service, passing in the order details. This can include information like the buyer, seller, and amount. Request to PSP. The payment service then sends a payment registration request to the PSP. This request includes the payment details and a unique UUID for tracking the payment. Receiving token from PSP. The PSP responds with a token that acts as a temporary identifier for the payment. This token is essential for future interactions and validations. Storing the token. Before moving forward, the payment service stores the token in the database to ensure it is securely persisted. This is critical for ensuring transaction integrity. Display of PSP-hosted payment page. Once the token is safely stored, the client is redirected to the PSP-hosted payment page where the user can input their payment details, like credit card info. Payment processing by user. The user fills in their payment details, and the PSP processes the payment. The result of this operation determines the payment status: approved, declined, etc. Payment status from PSP. The PSP then responds with the payment status, and the client is redirected to a redirect URL. At this point, the user is informed of the payment outcome: asynchronous webhook update. In parallel, the PSP sends a webhook to the payment service with the payment status. This ensures the payment service has the most up-to-date payment information. The payment service listens for these events and updates the payment order status in the payment order table to reflect the actual payment status. Reconciliation process. Periodically, the system compares the data across different components, e.g., payment service, ledger, wallet, PSP, to ensure data consistency. This process helps in identifying discrepancies early and ensures all services are in sync, particularly useful for resolving data mismatches. Handling payment processing delays. Asynchronous communication. Payment services are highly asynchronous. We use technologies like Kafka to ensure that various components, such as the payment service, wallet service, and PSP, can communicate asynchronously without blocking one another. Retrying failed payments. Failed payments are handled through a retry queue. Payments that fail due to temporary issues can be retried. Dead letter queue. Payments that cannot be processed after several retries are placed in a dead letter queue for further investigation. Exactly once delivery mechanism at least. Once delivery. We ensure at least once delivery for all payment-related events, ensuring that no payment is missed due to network issues or service outages. This is typically handled by implementing retries with exponential back-off strategies. Idempotency. To avoid duplicate payments, we utilize an idempotency key. This ensures that even if the same payment request is retried multiple times, the same result is returned, and no duplicate charges occur. Consistency in different services. Payment service, responsible for managing all payment-related data. Ledger, maintains accounting data for transactions, ensuring financial records are accurate and balanced. Wallet, keeps track of account balances, which are updated once payments are successfully processed. PSP, executes payments and sends payment execution status back to the system, ensuring the payment transaction is fully processed. Payment security measures. We implement strict security protocols to protect sensitive payment data. This includes protection against eavesdropping on requests responses, e.g., by using HTTPS, data tampering during transmission, via encryption, man-in-the-middle attacks, using SSL, TLS encryption, data loss by backing up sensitive data and using redundancy, DDoS attacks by employing rate limiting and anomaly detection mechanisms, card theft by adhering to PCI compliance standards, fraud prevention by implementing real-time fraud detection tools and algorithms. PCI compliance. We ensure that the system complies with the payment card industry data security standards, PCI DSS, to guarantee secure handling of credit card information and prevent breaches. This high-level design and security considerations ensure that the payment process is secure, resilient, and can handle high volumes of transactions while maintaining consistency across services.